Oh, so much better. So we had, now let's quick recap. For those who were missing yesterday, they missed a lot. Man, they missed out on some big time stuff. We introduced the concept of the calculus ant, and you guys have become familiar with that. The calculus ant is a two-dimensional creature that lives on my two-dimensional board. They have a innate sense of where their XY coordinates are that define their universe. They crawl around on these two-dimensional functions. They're true explorers. They're always trying to seek new terrain. Sometimes, though, when they get in danger, we have to bring in the search and rescue. And a lot of times, if there's a blizzard or a fog or something, we got to be able to identify where to send the people to extract them. Okay, so this was the issue we were dealing with yesterday. We looked briefly at, I think the example we looked at yesterday was, first one, just quick recap, we looked at this function. I think I changed it a little bit, it was this. That was our function, right?
Yeah.
Okay, and prior to looking at, I really wish I kept that from yesterday, that was bad. Prior to even that one, can I go back one? Oh, why can't I? Oh. We even looked at an easier one. I don't even remember some line. I don't even remember which one it was, but we had some function.
1/2 x plus 1.
There it was. Okay, and so if this is the boring terrain that the ants were exploring, we said we just graphed that. And if the calculus blizzard blew through, the fog blew through, and the ant was stranded, but we knew his x-coordinate. He was able to transmit his x-coordinate. And his x-coordinate was, we'll try something different. Let's say his x-coordinate is 5. We know the function that defines the terrain. Thank you. Braden, I'll pass it back to Braden. If we know x is 5, where would we send the search and rescue team to pick him up? 3.5, good, because we're just plugging that x value into our function to find the corresponding y value, and we end up getting the point with coordinates 5, 7/2. Is that right? Yeah. Okay. 5, 7/2, and so we know if we go over 5 and up 3.5, we can tell them to go right there, because that's where the ant is. Okay, piece of cake. No big deal. It got a little trickier, however, when our terrain was not defined everywhere. Okay, and we kind of reminded ourselves about how this function would not exist. It's not defined at 1 because we can't divide by 0, right? There's 2 fundamental rules that govern whether or not we can have a real number at a location, right? We can't divide by 0 with real numbers, and we can't take an even root of a negative number. So in this case, 1 is not allowed. This function, and really what we ought to do here is probably say that, right? That's the one place where our function is undefined. And so this time, unfortunately, the ant didn't even show up, which means he must have fallen into that hole at x equals 1. And so we adopted the strategy of, how are we going to find out where he was? Well, we adopted the strategy of just making a table, right? And we looked at our table, and we looked at the values of the function as the x values approached 1, and we saw a pattern there, right? I can't remember, what did we say our answer was?
1, 2.
It was over 1 and up 2. Good. Okay, so on our table, we knew that that's what filled in that hole. Let's go back to this one, and let's take a quick look at how we would do this one graphically, because I have my graphing calculator installed now, and I want to show you something kind of important. So, wow, this chair is low. There, now I feel like a big boy. All right. Okay, now I've got the, not only do I have my calculator installed, it's bigger and better and in color this year, so that's good. Okay, so What is our function here? Oh, I got x squared minus 1. I can either use the, now, I'm not, I can't remember all the little tricks here, but it seems like, do you remember how we get to that? Isn't it like alpha F1?
Yeah.
There it is. And enter. Oh, that's not what I meant to do. Okay. Over x minus 1. Okay, so there's our function. In order to get the, well, what do we want our x and our domain and range to be? How about if we just say, let's let the window go, we'll let it go from -5 to +5. And then I'll just I set the x's, and then remember, if I hit zoom fit, which is zoom 0, if I go down the menu, show it to you once. Remember this stuff?
Yeah.
There's zoom fit. And I can just hit zoom 0 and it goes right to it. Oh. Okay, I don't really want that background image in there. I'm not sure. I was messing around with this thing yesterday, and now I don't know how to get rid of that stupid thing, probably. Let's see. It's awfully pretty, but oh my gosh. Are you kidding me?
I think you have to go to mode.
I have to go to mode?
Yeah.
Thank you. Normal, okay. Where in mode?
I lied, it's not there.
Oh, here it is. Go to second. Oh, hang on. Oh. You did lie.
It's in mode. Maybe through the word. Set the ramp on it.
Second format.
So, okay, that's what I was wondering, yeah. Second format. There we go.
Feelings.
Background image. Off. Excellent. I don't know, let's see. Oh my gosh. Got all kinds of images. Holy smoke. Oh, look at this. Look at these options we've got. Okay, that's a random assortment. There we go. Okay, now, well, what's going on here? You know, this looks like there's no background. That's true. But if you look at that graph, do you see the hole in that graph? Okay, it doesn't show up, does it? I mean, maybe. Well, I don't know. I can't convince myself that I see it. But we know where it is. It was at 1, correct? Coordinates were at 1, 2. So let's do this. Let's go ahead and move along the function. Now, there's a couple ways we can do this. I'm going to build in a little time here at the beginning to do some graphing calculator stuff with you, so everybody feels really comfortable with this. There's a couple ways I can explore a function. One of them is I can trace. Okay? Now, when I trace, the only problem with this is that when I trace, the size of the footsteps that I'm taking as I walk along the function is somewhat arbitrary. So I may not always land in the places where I want to land. If I walk along the function, you notice at the bottom it's giving me my x and y coordinates as I progress. Okay? And we missed it, didn't we? We stepped over the hole. Okay? That's okay. Right, so that's just because those little increments were just not conveniently spaced for us. But that's usually going to happen. I think trace is fairly worthless, honestly. There's a better way to do this. We can just go, if we go to the, let's see, if I go to second calc, there it is. Yeah, second calc value. If I do second calc value, and then I choose the x value to be, just for as an example, if I picked 0.5 and hit enter, it'll put me to that spot and it tells me the corresponding y coordinate. See that? That's kind of cool. It gives you the value of the function and it shows you on the graph where you sit on the graph. Okay. Say it again.
How'd you know what to put for X?
I just picked something randomly. Okay. Now, what if I think there's a shortcut for this too, if I can remember what it is. I think you go,
Just click trace.
oh, that's right. You click trace and then you type the value. So if I go 0.5 and hit enter, it takes me right there. That's quicker, okay? So let's see what happens if we go trace 0.9. Well, it's getting us close, isn't it, right? If I go trace 0.9999, it's getting right up next to that hole, but look what happens if I actually test the value of the function at 1. Trace 1, what happened? Doesn't exist. That's the calculator's way of telling you the function is not defined there. When x equals 1, there is no y value because the function doesn't exist. Okay? Make sense?
Yeah.
Okay, so we used the table approach yesterday. Graphically, all we'd have to do is just maybe back off by a tiny little amount or go forward by a tiny little amount and just see what's the missing value. Okay, does that make sense? What value is it approaching? Do you see a weakness in this approach? What is it? Say it again. Yeah, there's an infinite number of values. We lucked out. We got one that falls right on an integer, and so we can see that pattern pretty easily. But what if that were falling on some bizarre decimal and the function weren't linear? So we're approaching that value more quickly on one side than the other side. Does that make sense? That makes it kind of difficult to get an exact value, doesn't it? Yeah. We could get pretty close, and and for the most part, we can just get as close as we need to be, but it's not exact, is it? Okay. All right, so just keep that in mind. Okay, so we moved on. I think we left off with, an ant on different function. He was on, yeah, see, you tell me if this is the one I used. I think this is it. F of x equals, that one?
Yeah.
Okay. And we even talked about how we could determine what's the value of x that makes the bottom 0, right? We set the bottom equal to 0 and solve. We got an answer of 0. Yeah. So we know here that this function is undefined at 0. Well, turns out the ant must have fallen in the hole because he doesn't show up on radar anywhere, right? So we got to go find out where that is. We could graph this thing, that's fine. Let's take the table approach with the calculator this time, though. Okay? So we want to pick values surrounding 0. Okay? So you're probably gonna, you've done this more recently than I have, I bet. So you're probably gonna have to help me out with this. But let's see if together we can figure out how to do this. So the way I would recommend here is you go into y equals and you set up the function. Okay, so alpha f1. Okay, and we had x divided by the square root. There, I see it there. Second x squared. There we go. Thank you. X plus 1 minus 1. There we go. Okay, so x plus 1, get out of the radical, minus 1. Enter. Okay. And we go to table. Okay. And on table now, we get to do some things here. On table, actually, before we do that, let's go to table setup. So second F2. Let's set up our starting value. Probably not 0, because 0 is the value we want to kind of explore, isn't it? So why don't we go like -1 maybe? That sound good?
Wait, so how do you get there?
You go second, tape, right there, it says table set in blue on mine.
Can you just like scroll up? You have like.
You can. Yeah, I think you can scroll up. Yeah. So we can, okay, let's try that. We can even just leave it at 0. Now, the delta table, though, this is something that we do want to change. We want that delta table to be maybe pretty small, right? So maybe let's pick something like 0.0001. How about? Okay.
Why do we want that small?
Well, we want it small because we want to get pretty close to the value that we're exploring, right? And now if we go, do I have to hit enter? I don't even know if I do, but I guess it's fine. Yeah, maybe you do have to hit enter.
Did you say -1 for the table to start?
You can, if you want to start it somewhere else, you can. Ryan he made the suggestion. We can just scroll up beyond it anyway, so it's probably fine. And now if I go second table, there you go. Okay. As expected, we get an error at 0, but as we get, now these are in scientific notation. I could probably make these display as decimals, but we don't need to. What is 1 times 10 to the negative 4? Yeah, 0.0001, right? And this is 0.0002. If I scroll upward, let's kind of put 0 in the middle. It's pretty clear we're approaching a value there, isn't it? What is it? Seems to be 2, doesn't it? Now, yeah, that's a 2, but I think the reason that's a 2 is because to within the number, the degree of precision that we're using on the calculator, maybe we can fix that. If we go to mode, oh, I've got it on float, which should have been okay. But how about if I go down and I go like, we'll do like fix 8, or I went too far. Fix 7, how about?
Float 7?
Well, instead of float, now it's going to fix 7 decimal places, I believe. It's in mode, yeah. So let's just see what that does. Now if I go back to table, it didn't fix things at all. Oh yeah, okay, well, it kind of did. We just can't see that many places on here. And I don't know if there's a way to fix that.
Click on the number. Like click on the point 0, 0, 0.
Yeah, like scroll over to the.
Yeah, and then
If you
it
scroll
does
over
way
to it,
more.
it shows you the whole thing.
Oh, it does. I got you. Okay, that's good. Oh, there you go. Perfect. Thank you. That's helpful. Everybody see that?
Yeah.
So then if you go down, it's only showing you so many decimal places, but now it's giving you the full deal here, right? So that's really not 2, okay?
Okay.
So that makes more sense, doesn't it? This is roughly 0.00005 above 2. If we go up this way, what do you know? It's roughly 0.00005 below 2. You know, give or take a little bit. It's not a linear function, but gives you a pretty safe bet that's darn close to 2.
Yeah.
Okay? So that's where we go look for this guy. Make sense? Okay. Questions? Well, he's hypothermic, but we're going to get him out of there. Okay. Let's try something different. Let's try, we can kill many birds with one stone here, so to speak. Okay, so let's go to another function. Let's try a different kind of function this time. Let's try a piecewise function. Okay? Let's try a function. We need some review of this anyway. This is good stuff. So let's take the piecewise function. F of x equals 1 when x is not 2, and f of x equals 0 when x is 2. Okay. Let's even try using, this is overkill, but I want to show you how to do this on a graphing calculator if I can remember. A year ago, I could have done this in my sleep, but now I probably can't do it when wide awake, so we'll see. I think this is how you do piecewise functions. We go up to y equals, and we go, I think you put it in parentheses. You go in parentheses, we would put y equals, oops, hang on, it was 1, I think, wasn't it? Pretty sure it was. Yeah, okay. So y equals 1. Close the parentheses, and then next to that in parentheses, you have to put the domain, okay? So the way that we would put that domain, we don't have the option, I believe, on the calculator of saying x.
I think you do. I think you got a math.
We can do x is not equal to 2? Okay, okay, let's try it. Our other alternative would just be to say x is greater than,
It's second math.
okay, okay, let's try that. We'll try it both ways. Yeah, this is good. I'm learning some stuff too. So you go to the test menu. Oh, you have to do x first. Whoops. X is, and then you go to the test menu to get all the inequalities. Oh, and there is a not equal to sign. Good. So x is not equal to, was it 2?
2.
Okay. Okay, now you have an option here. We could go down to the next function and write the other part of the piecewise function, but what I prefer to do is just add the second piece of the piecewise function to it right there. So then in parentheses we would put 0. That's the value of the function. You see the pattern? And then next to that in parentheses the domain of that part of that piece of the function. That would be when x equals, which probably have to go to test again. So you see where I'm getting that? Second math is the test menu. Okay. X equals 2. And let's just go ahead and go on our, we'll just go, how about if we just go, yeah, let's go graph. It's set up well enough for us. Okay. Well, it looks like it messed up, but it probably didn't, because remember that 1 point is just a pixel. It may not even amount to a pixel. So let's try our little test. What if we go trace 0? Works great. 0, 1. That's correct, isn't it? But what if we go trace 2? There it is. How about it? You can't see it very well, but it does have the point in the right place, doesn't it? You see that? Here, let's graph it once without the calculator, because we know what it should look like, and then we'll compare it to the calculator. What should this be? So x equals 1 every place except 2. That's what kind of function is that?
Okay.
Well, piecewise, but how about just that top piece, the function y equals 1? What's that? Straight line, straight horizontal line, right? So it looks like that, except I have to go back now and erase a point. So at x equals 2, it's kind of a big eraser. At x equals 2, we've got a hole. And down here is, when x equals 2, the value of the function is actually 0. Now that's not a very convenient way to write that hole, though, is it? It's hard to see. What should I put there instead? Open circle. Good. Yeah, that's our mathematical way of showing that there's a hole there. Okay, make sense? So this is a strange piece of terrain here. The ant is moving along the function, and then he drops down to here, right? Pops back up and walks along. But here's the problem with this. Unless we know what the function is, we have a real hard time guessing where he is, don't we? Right? We can't, this is different than the previous examples, isn't it? In the previous examples, we were always able to move, well, did I graph? I don't think I graphed this one, but it looked like this, right? We had, and then there was a hole out here at 1, 2, I think, right? So it looked like this. We were able to anticipate where that ant would be if that hole were filled in based on where the function was approaching from both directions, right? Doesn't happen here. So we would say, in other words, this function has a limit. Let's go ahead and attach let's kind of leave the world of calculus ants for a second and move into calculus. How would we say the process that we did for this function in terms of a calculus statement? Well, it would look like this. The limit, I'm going to write it out in words first, and then we'll abbreviate it. So we would just say the limit of f of x, as it's written there, right, of f of x, that's our function, as x approaches 1 is 2. Okay, how do we interpret that? Remember our example with the door yesterday. As we walk infinitely close to x equals 1, never reaching it, but as we walk infinitely close, what is the value of the function that we keep inching towards? Question? Yeah, go ahead. Does that make sense? Okay. It's important to know, though, here, you have to keep this in mind when you're, and tattoo these into your brain, these words. When you're dealing with limits in mathematics, a limit is a process of approaching something but never getting there, okay? So does the function exist at 1? No, it does not. Does the function's limit exist? Yeah, it does. We clearly approach a definite value, right? Does that make sense? Okay, what about this function here? Okay, does the limit exist? It does. The limit exists because as we walk along this function from either direction, there's a definite place that we think we're going to step on, isn't there? Where is that? At x equals 2, y equals not 0. We think we're going to land right there. In actuality, this is a bizarre function, and we just drop down to this other point. Does that make sense? So the value of the function is something different than what we would anticipate we're going to step on. So there is a limit, but the limit and the function just don't agree. Okay? The value of the limit, and if I go back here, let's abbreviate. I'm going to write this a little differently. We could summarize that whole statement down there, that wordy statement. We could summarize using mathematics as just saying LIM is limit. The limit of f of x, and we could even write it this way, the limit of that function, x squared minus 1 over x minus 1, as x approaches, the arrow means approaches, as x approaches 1 equals 2. Okay? The value that the ant would anticipate stepping on as he's walking along the function in the calculus fog, he can't see where he's going, but his built-in XY sensors would tell him, I'm going to land right there, right? When he actually steps there, he falls into a hole. He's not there, right? Does that make sense? Okay? But that's where he thinks he's going to be. Okay? Yes?
So in what instances does it, like the limit, not exist, you know?
Okay, let's talk about that,
Yeah.
where it doesn't exist. So it does exist here. It does exist there. That's an easy one, isn't it? Because this is a convenient place, because this time the ant steps exactly where he thinks he's going to step, doesn't he? The function exists there. Does that make sense?
Yeah.
Okay. The limit and the function agree. Here's a place where there's a limit, but the function is bizarre, and the value of the function is not where the limit anticipates it's going to be. Okay? Let's look at an example where a limit doesn't even make sense. Okay? How about some really weird terrain? Okay, how about this one? What if we do absolute value of x over x? Okay, first of all, are there any places where this function is undefined? Zero, okay? So we know the function doesn't exist
At 0.
at 0. Do we know what's going on there?
No.
Not necessarily. Okay, but we know it doesn't exist there. Okay, so let's graph this thing. Now, this is a piecewise function also in disguise. Remember how we deal with, and this goes back, it's been a couple of years since we've talked about it. You probably talked about it last year too, but how do we deal with an absolute value function? If we want to write that as a piecewise function, what is it? The absolute value of x takes on what values for what parts of its domain? Okay, so think about the job of an absolute value function. The job of an absolute value function is to make the argument positive always, right? So that's not a problem. When x is already greater than 0, the absolute value of x just equals x, right? It doesn't have to do anything there. Does that make sense? Okay. When, however, x is negative, what do we get? Yeah, we have to make it positive by multiplying by -1. Make sense? Okay. And then, of course, the in-between case where x actually equals 0, well, in this case, what is it? 0. Okay.
Are those commas or created?
These are commas. Sorry.
Oh, okay.
Those are commas. So, if we want to take this function as a whole, we're just going to divide each of these different behaviors of the piecewise function by normal x, right?
Yeah.
Make sense? So our piecewise function, then, if we go back to f of x, we could write it like this. When the absolute, okay, for values of x greater than 0, the absolute value of x would have just been an x, right? Make sense? So then we'd end up with x over x, which is 1. Okay? What about when x is less than 0? Then the absolute value of x would be a negative x. So -1. Negative x divided by x would be -1. And what about 0? Undefined. Doesn't exist at 0, right? So this is our piecewise function. There is no 0. If we graph that, it just looks like this, doesn't it? What do I do there?
Circle.
Good, okay. Because it doesn't have an endpoint there, does it? Right? Up here, it's going to be, what do I do there? Okay, so this is a function with a break in it. Can you tell me why a limit doesn't make sense here?
Because it's two-sided.
Yeah, we're getting two different guesses, aren't we? That can't be. As the ant walks in the fog backwards towards x equals 0, he anticipates when he gets to 0, stepping on a value of y equals 1, right? When he's walking to the right for values of x below 0, as he approaches 0, he anticipates stepping on a y value of -1. Well, that can't work. You can't be in those two places at once. And so there is no limit. There's no single limit that we can agree on, right? Make sense? So that is an instance where there is no limit at 0. Okay? Undefined. In general, anytime there's a break in a function, at the break in the function, the limit can't exist. Okay? And by a break, I mean an actual displacement of the function. You see that this is different than that. Agreed? Okay, in this case, walking from both sides, we can agree on where we think we're going to step. Make sense?
But then you fall in a hole.
We actually fall in a hole, but the limit doesn't care about what actually happens. The limit just cares about what you anticipate is going to happen. What actually happens could be very different, okay? Okay, so another case. What if we have, how much? 4 minutes? Okay, we can do it. Here's another case. Let's say we have a vertical asymptote at x equals 1. Right? And let's say the function's climbing to infinity on both sides. So it looks something like this. Make sense? Okay. Now it might seem at first glance that this is going to have a limit because you anticipate the same kind of behavior on both sides. But can you point to a place? No, you can't. As the ant approaches x equals 1 from the left side, where does he think he's going to step?
Keep going up.
Keep going up. right? The closer he gets to 1, the steeper the mountain gets. And so does he ever see the top? No.
Probably
The
not.
top is always infinitely high above him, right? And so he can never step on an identifiable point. And so for that reason, we would say no limit exists here, because there's no point on any scale of a graph that we could possibly produce where I could say that's the point where the ant thinks it's going to land on both sides. Okay? Make sense? So if you have infinite behavior in a function, that also would mean always no limit at that one point, right? And then the third one is really bizarre, really bizarre. This is kind of you don't see this one very often, but we got to talk about it. What if we had a function like f of x equals, it'd be like, have to be an argument of so how about we could use a sine or an exponential. We'll do sine of 1 over x. I think that would work fine. So if we do sine of 1 over x as x approaches 0, what's going to happen? Okay, now this is a really good one to look at, though. This is going to kind of stretch your brain a little bit, stretch your thinking. When you have a function of a function, a composition of functions like this, we have a sine of hand, right? But what's hand? In this case, hand is 1 over x. As x approaches 0, what's happening to the 1 over x behind my hand? It's getting bigger and bigger, isn't it? Because we know, just think about this generally, kind of, we don't have to pin anything down too precisely here. We know in general that a fraction is always going to be small when the bottom is big and the top is small, relatively speaking, right?
Yeah.
Top's a lot smaller than the bottom, the fraction is small. If the top is a lot bigger than the bottom, it gets big, right? So if the top is being pinned down at 1, but the bottom is getting very, 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 very small, that fraction ends up becoming huge, right? 1 divided by 0.00000001 is huge, right?
Yes.
So then as x approaches 0, this sine function is just seeing numbers that are just speeding up and getting bigger and bigger and bigger towards infinity, positive or negative, depending on the sign, right? Think what a sine function does. If we graph a sine function, you guys know this real well. Sine function just does that, right?
Yes.
So as we move out to the right and we're feeding the sine function values of x, it's always just going to oscillate between -1 and 1, right? Now as x approaches 0, that's like pushing the sine function out at the speed of light, right? In that direction, what's it going to see? Oscillations, always, right? That value is just going to oscillate between -1 and 1 increasingly rapidly as x gets bigger. Make sense?
Yeah.
So if we graphed it, it would look something like this. That function, well, it looked like this. You go just forever in there, right? This goes really fast. It never stops, right? Make sense? Okay. All right. Tomorrow we'll wrap this up and go to lab.